This is going to be the lecture over section 18.4. We'll be discussing capacitors. We'll get to 18.5 in a separate lecture. A capacitor is going to consist of any pair of conductors separated by a vacuum or an insulating material. The capacitance C is defined as the charge divided by the potential difference. Parallel plate capacitor is made with two parallel plates, each with area A separated by a distance d. If they're separated by a vacuum, the capacitance is going to be equal to the electrostatic constant times the ratio of the area over the distance between them. When capacitors with capacitances C1, C2, C3 are connected in a series, the equivalent capacitance is going to be given by 1 over the equivalent capacitance, which is going to be 1 over C1 plus 1 over C2 plus 1 over C3. That's when they are connected in series. When they're connected in parallel, you're just going to add the capacitances together. So sort of a picture of what's going on. You've got two conductors here. You've got a plate here that's got, that's labeled as plate A, area of capital A. Down here, you got a plate B with the same area. You got a positive charge here, you've got a negative charge here, so you've got a potential difference, and then you've got wires for both. So that's the kind of situation we're going to be looking at here. So a capacitor is just going to be a device that stores electric potential energy and electric charge. So a camera flash requires a brief burst of power much greater than the camera battery can deliver. That flash is going to be powered by a capacitor, which stores up energy from the battery and delivers it in a pulse when needed. Capacitors are also used in energy storage units for pulsed lasers, in computer chips that store information, circuits that improve the efficiency of power transmission lines, and thousands of other devices. The study of capacitors will help develop insight into the behavior of electric fields and their interactions with matter. So this figure shows high voltage capacitors that are used in power distribution systems, which you may have seen in substations like this. That will bring electricity to your home. In contrast, the capacitors in this type of arrangement are more representative of those things you found in common consumer electronics. So in principle, a capacitor consists of any two conductors separated by a vacuum or an insulating material. When charges with equal magnitude and opposite sign are placed on the conductors, an electric field is established in the region between the two conductors. And there's obviously a potential difference between them. In most practical applications, the conductors have charges with equal magnitude and opposite signs, and the net charge on the capacitor is 0. We'll assume throughout this section that that's the case. When we say that the capacitor has charge Q, we mean that the conductor at higher potential has charge Q, and the conductor at lower potential has charge minus Q. Keep in mind this discussion as we go on here. So you've got your conductor here, you've got your conductor here, you've got opposite charges, equal but opposite, and then you've got the electric field between them. So for a capacitor with a given charged surface area, the electric field at any point in the region between the conductors is proportional to the magnitude Q of the charge, which you might expect. It follows that the potential difference between the conductors is also proportional to Q. So if we double the charge on the capacitor, the electric field at each point and the potential difference between the conductors double. But the ratio of charge Q to that potential difference doesn't change. So therefore, the capacitance is defined as Q divided by potential difference. Units are going to be coulombs per volt or a farad. If you're going to find these in circuit diagrams, they're going to look something like this. In many applications, the most convenient units of capacitance are going to be the microfarad or the picofarad. So parallel plate capacitors. The most common form of capacitor consists of two parallel conducting plates. Each one of these is going to have an area A, and it's going to be separated by a distance d that is small in comparison with their dimensions. Nearly all the field of such a capacitor is localized in the region between the plates. You might have a little bit of fringing on the edges, but if the distance between the plates is small in comparison to their sides, you don't have to worry about that effect. The field between the plates is then uniform, and the charges on the plates are uniformly distributed over their opposing surfaces. So this is called a parallel plate capacitor. And you can kind of see the electric field here. So the electric field magnitude in the region between the plates is directly proportional to the electric charge per unit area of the plate. Since the charge on each plate distributes itself evenly over the surface that faces the opposite plate. This quantity is called the surface charge density. And you may have seen this before. It's a lowercase Greek letter sigma is what you use to signify that. So for a pair of plates with area A and total charges Q and minus Q, the surface charge densities are going to be Q divided by A minus Q divided by A. Gauss's law can be used to prove that for the parallel plate situation, the field magnitude E is related very simply to Q and to sigma. So the electric field here is going to be the charge density divided by the electrostatic constant, and that is also going to be equal to Q divided by E naught times A. So we're not going to derive that right now, but the constant here is equal to that particular value, and it was mentioned in 17.4. Recall that it's related to the constant K by K is equal to 1 divided by 4 pi E naught. The field is uniform. If the distance between the plates is D, then the potential difference voltage between them is going to be E times D, or this expression. So basically you take this and you just have a D multiplied by it. So the capacitance of a parallel plate capacitor in a vacuum is directly proportional to the area of each plate and inversely proportional to their separation. So the capacitance is Q divided by the potential difference, or this. Again, the units are farad. So this E naught is going to be the universal constant of nature, sometimes referred to as the permittivity of the vacuum. So you can see the units here of 1 farad and how that compares to several of the other units. Since 1 volt is going to be 1 joule per coulomb, this relationship is consistent with 1 farad being 1 coulomb divided by a volt. And then finally, the units of the permittivity constant is going to be this, 1 farad per meter. And you've got some problems there to work through.